Okay. Okay. Hi everyone. So good evening all. So first of all, let me know whether audio and video everything is clear. So first of all, let me know whether audio and video everything is clear. Okay. So I hope audio and video everything is clear, right? So if it is not clear, please give some comment in chat box, right? Okay. Okay. Yeah. So we are dealing with the capacitors. We are dealing with the topic of capacitors, right? So today we try to solve some problems based on these capacitors here, right? Okay. Okay. So let us take this problem. So we have solved already the same type of problem in the previous session also, right? In the last class also we have solved the same type of problem, right? So let us see what is the problem here. They have given is a capacitor of capacitance 1 microfarad can withstand a maximum voltage of 6 kilovolts. Okay, a capacitor of capacitance 1 microfarad can withstand a maximum voltage of 6 kilovolts, and the other capacitor of capacitance 2 microfarad can withstand a maximum voltage of 4 kilovolts. Another capacitor whose capacitance value is 2 microfarad can withstand a maximum voltage of 4 kilovolts. Then the series combination of the capacitor can withstand a maximum voltage of, okay. So if you connect these two capacitances in series, then what is the maximum voltage this series combination of capacitor can withstand? So that's what you have to determine. So option A they have given us 4 kilovolts, and option B they have given it as 6 kilovolts, and option C they have given it as 9 kilovolts, and option D they have given it as 10 kilovolts, right? Okay. So similar type of problem we have solved in the previous session also, right? Okay. Okay. Now see here. So now see here what they have given. So they have given two capacitors connected in series. So two capacitors are connected in series, right? And we have applied a voltage. Let us say we have applied a voltage of V across these capacitors, right? Okay. So let us say this is C1 and let us say this is C2. So C1 I am considering C1 as what? 1 microfarad. So this I am considering as C1, and 2 microfarad I am considering as C2, right? And this is 6 kilovolt, that is the maximum voltage across C1. So this I am considering as V1 maximum, and the maximum voltage across the C2 can be what? Can be 4 kilovolts. So this 4 kilovolts I am representing with V2 maximum, right? Okay. Okay. So here C1 value is equal to 1 microfarad, C2 value is equal to 2 microfarad, and the maximum potential that can be applied across the C1 is equal to 6 kilovolts, and the maximum potential that can be applied across C2 is equal to 4 kilovolts, right? So this is the data they have given. So in this case, what is the maximum voltage that you can apply across this series combination, right? So that is what they are asking, right? Okay. So now since it is a series combination, so whenever you apply a voltage here, so a part of the voltage will be dropped across C1. So that potential I am representing with V1, and remaining part of the voltage will be dropped across C2. So that I am representing as V2 here. That is nothing but V2. Right. Okay. Okay. So now see here. Now see here. Now what is V1 here? So V1. So now by applying voltage division principle here, I can represent V1 as what? V1 is equal to V into C2 divided by C1 plus C2. Yes or no? So this is equivalent to V into C2 value is equal to 2 microfarad and C1 value is equal to 1 microfarad. So what you are going to get? V into 2 divided by what? Divided by 1 plus 2, so that is 3. Okay, so you are going to get here 2V by 3 here. You are going to get here 2V by 3. So that is V1, right? Okay, next similarly, I can represent V2. As what here? V2 is equal to. So this is the voltage drop across C2. So now by applying the same voltage division principle, I can write V2 is equal to V into what? V into C1 divided by C1 plus C2. So this is equal to V into C1 is nothing but 1 microfarad and C2 is nothing but 2 microfarad. So I can write it as 1 divided by 1 plus 2, that is 1 by 3, which is equal to what? V by 3. Right. Now if you observe here, the total voltage here, the total applied voltage V is equal to what? Is equal to V1 plus V2. I can represent in this manner. Right. Now here this V2 is equal to what here? Is equal to V by 3. So this one I can represent in this manner here. See here. So I can write this as 2 into V by 3 into 1 by 2. So just I have multiplied with 2 and divided with 2. Right. Now in this case, I can represent this 2V by 3 here. This 2V by 3 is nothing but what? 2V by 3 is nothing but V1. So I can represent V2 in terms of V1. So how I can represent here? So I can represent this as V1 divided by what? Divided by 2. So this 2V by 3 is nothing but V1. So I can represent this V2 as V1 by 2. Right? Okay. Okay. Yeah. So see here. So this V is equal to V1 plus what? V2 I can represent in terms of V1 in this manner, that is V2 is equal to V1 by 2. So this is the total applied voltage, which is equal to V1 plus V1 by 2. Right. Okay. Okay. So now here as this voltage goes on increases here, the applied voltage goes on increases, so this V1 will also goes on increases. So as V1 goes on increases, this is nothing but what? V1 by 2 is nothing but V2. So this value will also goes on increases. Right. Okay. So V1 can be maximum. V1 maximum, it can be reached up to what? V1 maximum can be reached up to 6 kilovolts, and V2 maximum, that is the maximum potential that can be applied across C2 is equal to what? Is equal to 4 kilovolts. So this is what they have given. Right. Okay. So now let us assume V is increasing. So as V increases, this V1 is also going to increase. So as this V1 increases, this V2 value is also going to increase. Right. Okay. So now let us assume V1 has reached to. Let us assume here V1 has reached to. As V goes on increases, this V1 is also going to increase. Let us assume this V1 has reached to V1 maximum here. This V1 has reached to V1 maximum. So whenever this V1 reaches to V1 maximum, this V2 will reach us to what? This V2 will reach us to V1 maximum by 2. This V2 value will reach us to V1 maximum by 2. So V1 maximum by 2. So what is V1 maximum value? Is nothing but 6 kilovolts. Right. And here V1 maximum by 2, this value is equal to 6 kilovolts by 2. So that is equal to 3 kilovolts. Understood? So this is V2 value here. This is nothing but V2 value. Right. Now if you observe, this 3 kilovolts is less than what? This V2 is less than V2 maximum. This V2 is less than V2 maximum. Understood? Okay. Now what happens here? So as V goes on increases, at one stage V1 has reached to its maximum value, that is V1 maximum. So at this stage V2 value has become equal to what? 3 kilovolts, which is less than what? Which is still less than V2 maximum. Now if you further increase voltage here, if you further increase V, then V1 will try to increase further. That means it will try to increase beyond V1 maximum. So if it increases beyond V1 maximum, then the breakdown will occur and the capacitor will get burned away. Understood? Okay. So So you have to apply the maximum voltage without any breakdown here, without any breakdown. Understood? So that means the maximum voltage that you can apply, the maximum voltage that you can apply is nothing but what? Is nothing but you can go on increase this voltage until this V1 reaches to V1 maximum. So if you further increase this voltage, then this V1 will go beyond V1 maximum, but this should not be allowed, because if it goes beyond V1 maximum, then the C1 will go to breakdown. Understood? Okay, so the maximum safest voltage that you can apply is nothing but until this V1 goes to V1 maximum, right? Okay, okay. So therefore V maximum is equal to what? Is equal to V1 maximum plus what? Plus V2 voltage. V2 voltage is nothing but V1 maximum divided by 2. So this is nothing but V2, right? Okay, so this is the maximum voltage that you can apply without any breakdown, right? Okay, okay. So now see here. Therefore the maximum voltage that you can apply safely is equal to V1 maximum plus V1 maximum by 2. So that is 3 V1 maximum divided by 2. And what is V1 maximum here? V1 maximum is nothing but 6 kilovolts. So that is 3 into 6 kilovolts divided by 2, which is equal to what? Which is equal to 9 kilovolts, right? Okay, okay. So for this question, the correct answer is nothing but what? 9 kilovolts. The maximum voltage that you can apply across this series capacitor is nothing but what? Is nothing but 9 kilovolts. Okay. So up to 9 kilovolts it can withstand. So if you go beyond that, then this capacitor will go to breakdown. Understood? Okay. So it can withstand maximum up to 9 kilovolts. So this is the maximum voltage that you can apply. This is the maximum voltage that you can apply, right? Okay, okay. Right. So for this question the answer is 9 kilovolts, right? Okay. So we will see next question here. We will see next question. So see here, this is next question. So it is observed that the capacitance of an isolated sphere of radius, A is increased by n times when it is enclosed by an earthed concentric sphere of radius B. Then B by A equals, is equal to, right? Okay. So what they have given here is it is observed that the capacitance of an isolated sphere of radius A is increased n times when it is enclosed by an earthed concentric sphere of radius B. Then B by A ratio is equivalent to. So option A they have given it as n square by n minus 1. Option B they have given n by n minus 1. Option C 2n by n plus 1. In option D they have given it as 2n plus 1 by n plus 1. So you have to identify the correct option here, right? Okay, okay. So now see here. So what is the question they are saying here is isolated capacitor. So that means consider a spherical, they are saying isolated spherical capacitor, right? Okay. So isolated spherical capacitor, right? So let us say this is isolated spherical capacitor of radius. Its radius is A. Its radius is A, right? Okay. Okay. And the charge on this one is plus Q. Let us assume the charge on this one is plus Q. Let us assume, right? Okay. Okay. So we know that the capacitance offered by an isolated spherical capacitor is how much here? Is nothing but the capacitance of this one is equal to what? Is equal to 4 pi epsilon naught into A farads. Okay. So we know this one here. If you are having an isolated spherical capacitor, then due to the then the capacitance of that spherical capacitor is equal to what? Is equal to 4 pi epsilon naught into A, right? Okay, okay. Now now so I am considering so this is a spherical, this is a sphere, metallic sphere of radius, this is of radius a, right, and the charge on this one is plus q, right, and here this outer hollow sphere is grounded, right, and the radius of this hollow sphere, is b, right. Okay, so for this one here, the capacitance C, is given by what? Is given by, let us say this is C1 and let us say this is C2. So this is given by 4 pi epsilon naught into AB divided by B minus A, right. Okay, we know the capacitance offered by this capacitor and the capacitance offered by the isolated capacitor, isolated sphere, right. Okay, so for this one the expression is 4 pi epsilon naught into A, and for this one the expression is 4 pi epsilon naught AB by B minus A. See, if B tends to infinity here, then this will become equivalent to what? Equivalent to this one. Understood? Here if B tends to infinity, then the capacitance will become equivalent to this value, that is 4 pi epsilon naught into A, right. Okay, okay. So now see here. Okay, now they are saying that here in the problem they are saying that the capacitance of an isolated sphere of radius A is increased n times when it is enclosed by an earthed concentric sphere of radius B. Understood? Okay, so this is earthed concentric sphere of radius B, right. So the capacitance of an isolated sphere has increased by n times whenever it is enclosed by an what here? Enclosed by an earthed concentric sphere, yes or no? Enclosed by an earthed concentric sphere of radius B, right. So that means they are saying that C2 is equal to what? C2 is equal to n times of C1, right. Okay, so whenever this isolated sphere is enclosed by a earthed concentric sphere, the capacitance value has increased by n times. So that means C2 is becoming equal to what? N times of C1. So this is what they have given, right. Okay, okay. So which means C2 is nothing but what here? C2 is nothing but the expression for the capacitance in this case is nothing but 4 pi epsilon naught AB divided by B minus A, which is equal to what? Which is equal to n times of C1. So C1 is how much here? C1 is nothing but 4 pi epsilon naught into A. So here write down 4 pi epsilon naught into A, right. Okay. Now here 4 pi epsilon naught A, here 4 pi epsilon naught A will get cancelled. So therefore you are going to get B by B minus A is equal to what? Is equal to N. So from here you are going to get B equal to NB minus NA, right. Okay. Okay. So then I can write this as NA is equal to NB minus B, which is equal to B into N minus 1, right. So therefore B by A is equal to what? Is equal to N by N minus 1. So then the ratio of B by A is equal to what? Is equal to N by N minus 1, right. Okay, okay. So for this question, what is the answer here? B by A ratio is nothing but N by N minus 1. Okay, okay. So for this question, the answer is N by N minus 1. So that is option B. So option B is correct for this question. That is N by N minus 1. Okay, okay. So with this, we have completed this problem, right? Okay. So next, the other model that we can expect in capacitors is so here I am going to explain two cases here. So in those two cases I am going to explain 4 experiments. Understood? Okay. Okay. So now see here under case 1 I am going to explain 2 experiments. Under case 2 I am going to explain another 2 experiments. So totally 4 experiments. See, most of the conceptual questions are asking based on this 4 experiments here regarding capacitors, right? Okay. Okay. So now let us say case 1. I am considering case 1, right? So in case 1 you are going to have 1 and 2 experiments, and again I am going to take a case 2. So under case 2 you are going to have another 2 experiments. So totally you are going to have 4 experiments. Understood? So most of the conceptual questions in capacitors have been asked based on these 4 experiments, right? Okay. Okay. Now see here case 1. So here this is a capacitor is connected to power supply. PS means power supply here. So capacitor is connected to power supply and once it gets charged, then the power supply is removed. Okay. So capacitor is connected to power supply. So once it is connected to power supply means what? It is getting charged. So and once it gets charged, then the power supply is removed. Okay. Capacitor is connected to power supply, and once it gets charged, then the power supply is removed, right? So in this case the first experiment is what happens in this case the first experiment is if the distance between the capacitor plates is changed, then what happens to potential V, electric field E, capacitance C, and the energy stored in the capacitor, which I am representing with W, right? So this is the first experiment we are going to do. So what I am saying here is the capacitor is connected to power supply and it is getting charged. So once it gets charged, it is disconnected from the power supply. Understood? Okay. So once it gets disconnected after charging, it is going to get disconnected from the power supply. So once it gets disconnected, then what happens if the distance between the capacitor plates is changed? What happens to V, what happens to E, that is electric field, and what happens to capacity of a capacitance, and what happens to the energy stored in the capacitor? Understood? So we have to determine all these things. Right. Next, in this case, the second experiment here. In this case, the second experiment is if we insert a dielectric material, between the capacitor plates, okay, if we insert a dielectric material between the capacitor plates whose permittivity is epsilon is equal to epsilon naught into epsilon r, whose permittivity is epsilon equal to epsilon naught into epsilon r. So then what happens then what happens to V, comma E, C and W. V means potential across the capacitor, E means electric field between the capacitor plates, C means capacitance of the capacitor, and W means the energy stored in the capacitor. Okay, so these are the two experiments we are going to see under this case 1. Under this case 1, these are the two experiments we are going to see, right? Okay, okay. So next here. So next we are going to take case 2. Okay, so in case 2, the capacitor is connected to the power supply. The capacitor is connected to the power supply, and once it gets charged, the power supply is not removed. So once the capacitor gets charged here, then also the power supply is not removed. So that means in this case always the capacitor is connected to the power supply. So that's what you have to understand. So here the capacitor is connected to the power supply, it gets charged, after that the power supply is removed. But here the capacitor is connected to the power supply, it gets charged. Once it gets charged, then also the power supply is not removed. Understood? So that is the difference between case 1 and case 2, right? Okay. So now here you are going to have another experiment, that is third one. So here we will see if the distance between the plates, the same thing here, if the distance between the plates is changed, then what happens to potential, electric field, capacitance and energy stored, right? Next, fourth experiment, the same thing here. If we insert a dielectric material, between the capacitor plates, whose permittivity is epsilon equal to epsilon naught into epsilon r, then what happens to potential, electric field, capacitance and energy stored in the capacitor. Understood? Okay. So under case 1 we are going to deal with these two experiments. Under case 2 we are going to repeat the same thing here. So under case 2, so I am naming this as third one and this as fourth one. Okay. So these are the different experiments that we are going to conduct in case of capacitors, right? Okay. Okay. So now let us check the first one here. Let us see the first one. Okay. So that is case 1. Let us take case 1. Right. So let us take case 1. In case 1, let us take the first experiment. Okay. Okay. So now see here. So here what they are saying here is you are having a capacitor, and this capacitor is connected to a power supply, right? Let us say it is connected to some battery having a potential V, and now it gets charged. Whenever it is connected to power supply, it gets charged. Understood? Okay. So let us say here on this plate the positive charge will get accumulated, and on this plate negative charge will get accumulated. So the potential that is developed across this capacitor is also equivalent to what? Is also equivalent to V. And let us say the distance between the capacitor plates is D, right? Okay. So once it gets charged here, once it gets charged to this battery potential, so then we can remove, then we are removing this power supply. So now if you remove this power supply here, if you remove this power supply, now you are removing this power supply, right? So if you remove this power supply, so if you remove this power supply, the potential drop across the capacitor plates will be V, and the distance between the capacitor plates is D. Understood? Okay. And here you are having the charge on the capacitor plates is present, right? Now here in this case, once it gets charged and once you remove the power supply here, so that means now it is not forming any closed path. It is not having any closed path. So which means whatever the charge that is present on the capacitor plates is getting trapped. Yes or no? The charge on the capacitor plates has no path to move. Yes or no? The charge on the capacitor plates is not having any path to discharge. So which means the charge on the capacitor plates is trapped. So whatever you do here, so that means if you want, you can change the distance between the capacitor plates, or if you insert the dielectric material between the capacitor plates, whatever you do, the charge on the capacitor plate is not going to change, because this charge on the capacitor plate, for this charge on the capacitor plate has no path to move. So which means always whatever you do, the charge on the capacitor plates will be fixed in this experiment. So that is in case 1 here. In case 1, the charge on the capacitor plate will be always fixed, right? Okay. Okay. So that means in this experiment, the charge on the capacitor plates is fixed. The charge on the capacitor plates is fixed. So that is what you have to keep in mind. So whatever you do, the charge is not going to change because it has no path to move. Right? Okay. Dev Shukla, it is live only here. Right? It is not recorded, it is live only. Right? So maybe you are getting that doubt because of no audience. Yes or no? Okay. So nobody has commenting something in chat box, right? So that's why maybe you are getting that doubt. Okay. But actually it is live only, right? Okay. Okay. Right. Okay. So we are teaching just because at least after live session, at least if 1 or 2 persons see the lecture, they have to understand and they have to gain some knowledge from these lectures. Okay. So that is what our intention, right? Okay. Okay, the charge is fixed on the capacitor plates in this experiment. So here in the first experiment, they are saying that if the distance between the capacitor plates, is changed, then what happens to the potential, electric field, capacitance and energy stored in the capacitor. So what happens, we will see here, right? Okay. Okay. So now in this case here, so now here in this case, let us say okay. So let us say here in this case, wait. Okay. So what they are saying here is, so in this case, if you change the distance between the capacitor plates, If you change the distance between the capacitor plates, then what happens to the potential and what happens to the electric field? What happens to the electric field between the capacitor plates, and what happens to the capacity of a capacitance, and what happens to the energy stored in the capacitor? So this is what we have to determine. Okay, okay. So if D changes, right, in this case, if D changes, what will happen? We will see. Right. So first we will check for potential here. First we will check for potential. So we know that V, the potential across the capacitor plates, V is equal to what? V is equal to E into D, where E is the electric field between the capacitor plates and D is the distance between the capacitor plates. Right. Okay. And we know that the electric field between the capacitor plates, E, is given by what? Is equal to rho s by epsilon. Is equal to rho s by epsilon. Right. Okay. So generally, with the help of this expression, generally what the students will do here is, if D changes, they will say, if D increases by 2 times, they will say V also increases by 2 times. You should not tell like that here, because here apart from D, you are having E also. So you have to check whenever D changes, what happens to E, that also you have to check. So based upon that, you have to judge what happens to potential. Understood? Okay, okay. So now here the electric field between the capacitor plates is given by what? Is given by this expression, that is rho s by epsilon. Understood? Okay. Now here in this experiment, the charge is fixed here. In this experiment, the charge is fixed, which means rho s is fixed, which means the charge density on the capacitor plates is fixed. It is not going to change. Now here you are changing only D, that is the distance between the capacitor plates. Understood? But you are not changing the medium between the capacitor plates. If you are not changing the medium between the capacitor plates, then epsilon will remain same. So which means epsilon is also what? Epsilon is also fixed. You are not changing the medium between the capacitor plates. You are just changing the distance between the capacitor plates. Right. So and hence epsilon is also fixed. So since rho s is fixed, epsilon is fixed, this electric field between the capacitor plates will also be fixed. Right. Okay. Now if this electric field is fixed here, then that means this is constant. Electric field will become constant. So which means V is proportional to what? V is proportional to D. So that means in this case, as the distance between the capacitor plates changes, the potential is also changes by the same proportion. Understood? Okay. Okay. Right. So potential is proportional to what? Potential is proportional to distance. Right? Okay. Okay. So in this experiment, if you change the distance between the capacitor plates, the potential across the capacitor plates is also going to change. Right? Okay. So next. So we have seen what happens to potential, and what happens to electric field here? What happens to electric field? So electric field between the capacitor plates is equal to what? Already we have done here. Yes or no? The electric field between the capacitor plates is equal to rho s by epsilon. Here the charge is not going to change, so that means rho s is fixed. Medium is not changing, so epsilon is also fixed. So electric field is also fixed. So that means in this case, if you change the distance between the capacitor plates, electric field is not going to change here. The electric field between the capacitor plates will remain same. It is not going to change. Okay. So this implies electric field remains same. It is not going to change. Right? Okay. So next. So once potential is completed, then electric field, then what is present here? Capacitance. You have to check for capacitance. Right? Okay. Okay. So third one is capacitance. So that is C. Okay. We can write C is equal to what? C is equal to Q divided by what? Q divided by V. So in this experiment, Q is what? Q is fixed here. Q is fixed. Right? Okay. And this V I can write it as Q is fixed here. V I can write it as E into D. So here we have seen that the electric field is also fixed. So that is electric field will also remain same. Right. If Q is fixed, electric field is fixed, then capacitance is inversely proportional to what? Inversely proportional to distance between the capacitor plates. Right? Okay. Okay. So that means if the distance increases, in this experiment, if the distance increases, the capacitance is going to decrease. And in this experiment, if the distance decreases, then the capacitance is going to increase. So that's what you have to understand from here, right? So next, you have to check for what happens to energy stored within the capacitor, right? So that is nothing but fourth one here. So what happens to the energy stored within the capacitor here? We know that the energy stored within the capacitor is given by, I am representing with W, which is equal to what? Which is equal to half into CV square. So now this I can represent in this manner. See here, C is nothing but Q by V. I can represent C is nothing but Q by V. So here V will get cancelled. So I can represent this as half into Q into V. Half into Q into V. Now we know that in this experiment the charge Q is fixed. The charge Q is fixed, and this V I can represent it as what? Half into Q fixed, and V I can represent it as E into D. So E is also what? E is also fixed, right? So Q is fixed, E is fixed. So energy stored within the capacitor is proportional to what? Is proportional to D. Yes or no? Okay. So I can say here the energy stored within the capacitor is proportional to what? Is proportional to distance between the capacitor plates, right? So that means as the distance increases, the energy stored in the capacitor is also going to increase. If the distance decreases, then the energy stored within the capacitor is also going to decrease in this experiment. Understood? Okay. So if you connect the capacitor to a power supply, once it gets charged, now you are removing the power supply. So in this case, the charge on the capacitor plates will get trapped. That means they are not having any path to discharge. Understood? So whatever you will do here, the charge on the capacitor plates is not going to change. Okay. So based upon that, we have seen what happens to potential, and what happens to the electric field, and what happens to the capacity of a capacitance, and what happens to the energy stored in the capacitor. So this is what we have seen here, right? Okay. So so this is with respect to the first experiment, right? Okay. 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 See, based on this, they have asked you a question in gate here. Now you can easily tell the answer. See here the question. So this is the question they have asked here in gate. This is the question they have asked in gate. Now you can easily tell the answer for this question. See here what they have given. The parallel plate capacitor shown in the figure has movable plates. So let us draw here. They have given this figure here. So this is the capacitor. This is the capacitor, and the distance between the capacitor plates is D, right? So this is the diagram they have given. So let us say this is the figure they have given, right? Okay. So the parallel plate capacitor shown in the figure has movable plates. The capacitor is charged. The capacitor is charged so that the energy stored in it is E. Now they are representing the energy with E here. We have represented energy with W, but here they have represented the energy with E. So don't confuse it with electric field. Understood? So they have represented the energy stored with E, right? When the plate separation is D, the energy stored is nothing but E. The capacitor is then isolated electrically, and the plates are moved such that the plate separation becomes 2D. See here, what do you mean by when the plates, what do you mean by the capacitor is then isolated electrically? What do you mean by this here? The capacitor is then isolated electrically. What do you mean by that? So isolated electrically means you have removed the power supply. Understood? You have taken, they have taken the capacitor, they have charged the capacitor, right? So once they have charged the capacitor, the energy stored within the capacitor is nothing but E. Now what they have done? Now they have isolated electrically. So that means they have removed the power supply. So once they have removed the power supply, then what they have done is they have changed the distance between the capacitor plates to 2D. Then in this case that means at this new plate separation, what is the energy stored? What is the energy stored in the capacitor? So this is what they are asking, right? So what is the energy stored in the capacitor here? Tell me. What is the energy stored in the capacitor? Force is not Dev Shukla, force is not asked between. Not force here. They are asked to determine what? They are asked to determine the energy stored within the capacitor. So once this is increased to 2D, once the separation between the plates is increased to 2D, then what is the energy stored in the capacitor, right? Okay, so it is very simple here. See here, it is similar to the first experiment, yes or no? What they have done, they have taken the capacitor, they have connected it to power supply. Let us say they have connected to some power supply and it is charged to some potential V, and in this case the energy stored is equal to half into CV square. Let us say the energy stored is equal to half into CV square. So then what they have done here, they have removed the power supply here, they have removed the power supply, right? They have removed the power supply. Once it gets charged, they have removed the power supply, and now they have increased the distance here. Now they have increased the distance to what? To 2D. Now they have increased the distance to 2D, right? Okay. So now we know that in this case the charge will be what? In this case the charge will be always fixed. Understood? So just now we have seen here, in this first case, in this case here, okay, this will come under this case, right? So just now we have seen here the energy is proportional to what? Is proportional to distance between the capacitor plates. So in this case the energy is proportional to distance between the capacitor plates. Now here they have given that the distance between the capacitor plates is doubled, which means the energy within the capacitor plates will also be what? Will also be doubled. Understood? So that means you can say directly here the energy stored is proportional to D. So here the energy here the distance is doubled, which means the energy is also doubled. Understood? So I have represented with W here. So actually they have represented this with the symbol E. So E, which is nothing but energy. Okay, so energy is proportional to D in this experiment. So as D doubles, the energy is also going to double. So option A is correct for this question. Understood? Okay. So in this manner you can easily answer the question here. So if you understand these experiments, okay, then you can easily answer this type of questions, right? Okay. Okay. Right. Now, so in case 1 we have completed the first experiment. Next, what is the second experiment here? In the case 1, itself, what is the second experiment? Second experiment is if we insert a dielectric material between the capacitor plates whose permittivity is epsilon equal to epsilon naught into epsilon r, then what happens to V, E, C and energy? So this is what you have to check, right? Okay. So in case 1 we are seeing second experiment, right? Okay. Okay. So we know that once the capacitor is connected to power supply and it is removed from the power supply, then then this is the situation you are going to have. Once it gets charged, then it is removed from the power supply. So in this case, we know that the charge on the capacitor plates will be fixed. So you have to keep this point in mind here. So this is very, very important. Okay. So in this experiment, the charge Q is what? The charge Q is fixed. The charge is trapped on the capacitor plates, Q is fixed. It is not going to change. Right? Okay. Okay. So now let us say here, let us say the medium here is air medium. Let us assume it is epsilon naught. Let us assume it is epsilon naught. Okay. Now what they have done here is if we insert a dielectric material between the capacitor plates whose permittivity is epsilon equal to epsilon naught into epsilon r, then what happens to V, E, C and W? And here you can make a note that epsilon r is greater than what? Let us say epsilon r is greater than 1. Right? Okay. Okay. So now between the capacitor plates, now between these capacitor plates, right? So the distance here is d. Now you are not changing distance here, right? What you are doing? You are inserting a dielectric material between the capacitor plates. You have inserted a dielectric material between the capacitor plates, and its permittivity epsilon is equal to what? Epsilon naught into epsilon r, and here epsilon r is greater than 1. So here it is epsilon naught. Now you have inserted a dielectric material between the capacitor plates, right? So whatever you do here, whatever you do, the charge on the capacitor plates is not going to change. So that's what you have to keep in mind, right? Okay. So in this experiment, Q is what? Q is always fixed. Now we will check what happens to potential, electric field, capacitance and energy, right? Okay. So now first one is potential. So let us say V. So V is equal to what? V is equal to E into D, right? Okay. So now see here. So now here we are not changing the distance between the capacitor plates. So here also it is D and here also it is D. So we are not changing the distance between the capacitor plates. So that means D is fixed. D is fixed, right? Okay. Next, what is electric field here? Electric field between the capacitor plates is equal to what? Rho s by epsilon, right? Now here epsilon is nothing but epsilon naught into what? Epsilon naught into epsilon r. Okay. So which means here the epsilon value has increased by epsilon r times or not? Yes or no? So here in this case, initially epsilon is equal to what? Epsilon naught. Now epsilon has become epsilon naught into epsilon r. Yes or no? Okay. So that means epsilon has increased here. Epsilon has increased by epsilon r times. Now here rho s is nothing but what? Q is fixed means rho s is fixed. Okay. Okay. So this epsilon value, or I can write in this manner, right? So here this is epsilon. So here epsilon is equal to epsilon naught into epsilon r. So which means epsilon has increased by epsilon r times. Understood? So if epsilon increases, what happens here? The electric field is going to decrease. Okay. So if the electric field decreases, then the potential is going to what? If the electric field decreases, then potential is also going to decrease. So, or I can say, since D is fixed here, I can say simply V is proportional to what? V is proportional to electric field, and here from here I can say E is inversely proportional to what? Inversely proportional to epsilon. Yes or no here? I can say E is inversely proportional to epsilon, because rho s is fixed. I can say E is inversely proportional to 1 by epsilon, right? So which means I can say, since E is inversely proportional to 1 by epsilon, I can say V is also inversely proportional to what? V is also inversely proportional to epsilon. Yes or no here? Yes or no? Okay. Okay. Or if you want, I can write in another manner. See here, I can write in this manner. See. So V is equal to what? V is equal to E is nothing but rho s by epsilon into D. So here rho s is fixed. D is also what? D is also fixed. Understood? So if these two are fixed, then V is inversely proportional to what? Inversely proportional to epsilon. Okay, so if epsilon value increases, the potential is going to decrease, right? Okay, okay. So now, so this is what happens to potential whenever you insert a dielectric material. Next, what happens to electric field here? So this is the first one, right? Next, second one, what happens to electric field? So already we have determined here what happens to electric field. So electric field between the capacitor plates is equal to rho s by epsilon. Since in this experiment rho s is fixed, so this implies the electric field is inversely proportional to epsilon, right? Okay, okay. So we have observed what happens to electric field also, right? Okay. Next, so V completed, E completed. So next, third one, capacitance. What happens to capacitance? So C is equal to Q by V, and here in this experiment Q is what? Q is fixed. Q is fixed. So this is equivalent to, I can write it as Q fixed, V I can write it as E into D, E into D, and this one I can write further in this manner, Q fixed, E is nothing but what? Rho s divided by epsilon into what? Into D. Okay, so this I can write again as epsilon into Q fixed divided by rho s into D. Okay, okay. So here rho s is what? Rho s is fixed. Q fixed means rho s is also fixed, right? And here D is also what? D is also fixed. So C is proportional to what? C is proportional to epsilon. So in this case you are going to get C proportional to what? C proportional to epsilon, right? So that means the capacitance, if the permittivity increases, then the capacitance is also going to increase, right, in this experiment. Next, what happens to energy? Energy stored in the capacitor. So that is fourth one. So W, energy stored in the capacitor, I can write it as half into CV square. This I can write it as half into Q into V, and here Q is fixed, right? Okay, okay. And this V I can represent as what? This V I can represent it as rho s divided by epsilon into D. Okay, so this V I can replace with rho s by epsilon into D. Okay, so here rho s is fixed, D is also fixed, right? So therefore I can say energy is inversely proportional to what? Is inversely proportional to epsilon. Energy is also inversely proportional to epsilon. Okay, so these are the conclusions we can make here in this experiment. Yes or no? Right. Okay. See, there is no need to remember anything here. Just I am explaining how you have to analyze what happens to potential, what happens to electric field, what happens to capacitance, what happens to energy. Right. So just how to analyze all these things, that's what I am explaining here. Right. So whenever they ask some problem, you have to identify it comes under which experiment. So once you understand that, then you can easily analyze these things, right? Okay. Okay. Next here, next. So next case 2. So case 1 and case 2, case 1, in case 1 first experiment and second experiment is completed. Next we will go for case 2. So in case 2 we are having 3 and 4, right? So we will take case 2. Right, okay. Right. So in case 2 we will see third experiment here. So what is case 2 here? So capacitor is connected to the power supply and it gets charged. Once it gets charged also, the power supply is not removed, right? Okay. So in this experiment here, so that is case 2. In this experiment you are having a capacitor and this capacitor is connected to what? Is connected to some power supply. Let us say this is plus or minus V. I have connected to some battery, right? So once you connect this to battery, what will happen? This capacitor will get charged. So here you are having, let us say, plus positive charge, and here there develops a negative charge, and the potential between these two is nothing but, let us say, V, right? Okay. So this capacitor will be charged up to what? Up to the battery potential V. Okay. Okay. So now here in case 2, I am not removing the power supply. Once the capacitor gets charged, okay, I am not removing the power supply. So the power supply is always connected to this capacitor. The power supply is always connected to this capacitor. So which means always the potential across this capacitor is not going to change. Yes or no here? Yes or no? So in this experiment, the potential across the capacitor is not going to change because it is connected to what? It is connected to the battery. Understood? So it is always connected to battery. So this battery will try to maintain the potential across the capacitor equivalent to what? Equivalent to V. Right. So always in this experiment, what is fixed here? V is fixed. V is fixed. So that means whatever you do, so that means you can change the distance between the capacitor plates, or you can insert the dielectric medium between the capacitor plates. Whatever you do, the voltage will try to be fixed. The voltage is not going to change. So this try to maintain the same as battery potential. Understood? It should not change. So that's what you have to understand here. Okay. So in the previous case here, that is in case 1, what is fixed here? The charge on the capacitor plates is fixed, and in this experiment, what is fixed here? The potential across the capacitor plates is fixed. Right. Okay. Okay. Now see here. Now see here. So in case 2, this is the experiment we are going to see. So that is, if the distance between the plates is changed, then what happens to potential, electric field, capacitance and energy. Right. Now here let us say the distance here is D. Okay. So now we will see if D changes. If D changes, so then what happens we will see. Right. So if D changes, we have to check what happens to V, what happens to E, what happens to C, what happens to energy. Right. Okay. Okay. So first is V. So V is the potential across the capacitor. V is equal to what? V is equal to E into D. Okay. So in this experiment, we know that V must be what? V must be fixed. Always V must be fixed. Whatever happens, V must be fixed. Right. Here we are saying that D is changing. So if D changes here, then V has to change or not? But in this experiment, V is fixed. Right. So here D is changing. So let us assume if D is increasing, then correspondingly this electric field has to decrease by the same proportion, such that it is going to maintain the potential constant. Then only the potential will be fixed. Understood? One thing is for sure, in this experiment the potential across the capacitor must be fixed. Understood? So even if you change the distance, the potential must remain same. So that means if suppose D is increasing, then correspondingly the electric field has to decrease by the same proportion. So only in that case it can maintain the potential as fixed. Understood? Okay. So now actually what is happening here, we will see here. We will try to analyze what is actually happening here. Right. So here V is equal to what? V is equal to E into D. V is equal to E into D. So now see here. Now let us assume D is increasing. We are just analyzing here what is happening, why the V is becoming fixed in this case. That's what we are going to analyze here. Right. Now here V is equal to E into D. So now let us assume distance D is increasing. So whenever D is increasing, the potential will also tries to increase here. at that instant the potential will also tries to increase. So that means the potential here is trying to increase. So whenever the potential here is trying to increase, then the potential across the capacitor becomes greater than what? Greater than the potential across the battery. So in this case what will happen here? Since this potential is trying to increase when compared to the battery potential, what will happen? So it is going to supply the charge carrier. Since it is at higher potential and lower potential, it is going to supply the charge carriers to the battery. Yes or no? It is going to supply the charge carriers to the battery. So if it is supplying the charge carriers to the battery, then the charge on the capacitor plates is going to decrease. Yes or no? And here we know that the electric field is equal to what? Rho s by epsilon. Here you are not changing the medium between the capacitor plates, which means epsilon is fixed in this case. Understood? Okay, but here whenever D is increasing, V is trying to increase. So if V tries to increase, the potential here is trying to become greater when compared to the battery potential. So because of this potential difference, what will happen here? The charge on the capacitor plates will move to what? Will move to battery, or the charge on the capacitor plates will be supplied to what? Some part of the charge will be supplied to battery until the potential across the capacitor and the potential of battery both becomes what? Both becomes same. Understood? So this charge transfer will take place until the potential here and the potential here will become same. Right? Okay. Okay. So that means here the capacitor is supplying the charge here. The capacitor is supplying the charge to the battery, which means rho s is going to what? Rho s has to decrease. Rho s has to decrease. So if rho s is decreasing, the electric field has to decrease. Right. So the electric field is decreasing. So here the electric field has to decrease by the same proportion here. By the same proportion. Understood? So then such that here if electric field decreases, then the potential will also decreases by the same proportion, such that the potential will become what? Will remain same. Right? Okay. So in this case what is happening? So D is changing. If D increases, the electric field is going to decrease by the same proportion. Thus, it is going to maintain the potential as constant. Right? Okay. So during this process, this is what happening. Right? Okay. Okay. So I hope this is crystal clear here. Right. Next we will see this is first. This is what happens to potential we have seen. So next what happens to electric field? So electric field is equal to what? Is equal to rho s by epsilon. Rho s by epsilon. Right? Okay. See here there is no restriction on the charge on the capacitor plates. Yes or no? Now it can change here because now it is having a closed path. Now the charge is having a closed path, so it can discharge. Understood? Okay. So and hence in this experiment Q is not fixed. What is fixed here? V is fixed. Right? Okay. So keep that point in mind. So the electric field is equal to what? Rho s by epsilon. Right? And here epsilon is what? Epsilon is fixed. But here rho s can change. Rho s can change. So this implies E is proportional to what? E is proportional to rho s. That is surface charge density. Right? Okay. Okay. So now if rho s decreases, the electric field is also going to decrease. Right? So E is proportional to rho s here in this experiment. Okay. Next third one. So potential, electric field, and then capacitor. So capacitance C is equal to what? C is equal to what? I can write Q by V. Right? Okay. Now here in this experiment, V is what? V is fixed. But the charge on the capacitor plates is not fixed. Understood? Okay, it can vary. So now from this I can say C is proportional to what? C is proportional to Q. So if the charge changes, the capacitance is also going to change. So in this experiment, what is happening? As the distance increases, if suppose the distance is increasing, then the electric field is going to decrease by the same proportion. Understood? Okay. Thus maintaining the potential constant. And here during this process, what is happening here? The potential here is trying to increase. So here the potential is greater when compared to this one. In this case, the charge is supplied from the capacitor to what? From the capacitor to battery. So that means the charge on the capacitor plates is decreasing in this case. Okay, okay. So that's what you have to understand. Right. Next, fourth one. So next, fourth one. Energy stored in the capacitor, W is equal to what? Half into C V square, which is equal to, I can write it as half into Q into V. So here V is what? V is fixed. V is fixed. So which means W is also proportional to what? W is also proportional to charge. W is also proportional to charge. Understood? Okay? Okay. So in this manner you have to analyze. Right? Okay, okay. In the same manner, you can analyze what happens if D decreases. Right? In the same manner, you can analyze what happens if D decreases. Right? Okay, okay. So energy here, energy is proportional to what? Energy is proportional to charge. Right? Okay. Right. And one more conclusion here we can make here is, see here, V is fixed, you are having E into D, right. So from here I can write E is equal to V fixed divided by what? Divided by D. So from here I can say, since V is fixed, E is inversely proportional to what? E is inversely proportional to D, right. So this is also I can make one more conclusion. E is inversely proportional to D, right? Okay. Okay. See, there is no need to remember all these things here. Just I am explaining how to analyze the things. That's it, right? Okay. Okay. This analysis is very important, right? Next. So we have seen all the things: V, electric field, capacitance and energy. So next, in case 2, in same case 2, we have to see another experiment, right? So in same case 2, we have to analyze what happens. We have to analyze what happens if the medium between the capacitor plates is inserted with a dielectric material, right? So in the same case 2, if we insert a dielectric material between the capacitor plates whose permittivity is epsilon equal to epsilon naught into epsilon r, then what happens to V, E, C and W? So this is what you have to analyze, right? Now in this case, what you are doing here, so you are taking the capacitor, right, and it is connected to battery, that is power supply. So it gets charged and the potential across the capacitor plates is V. Now let us assume here the medium between the capacitor plates as air medium. So here epsilon is equal to, let us say, epsilon naught. Okay. Now here what I am doing here is I am inserting a dielectric material between the capacitor plates. I am inserting a dielectric material between the capacitor plates like this, right? This is the dielectric material that I have inserted between the capacitor plates. Let us say here epsilon, the permittivity of this dielectric material is equal to epsilon naught into epsilon r. Okay. So now what happens to V, E, C and W? That's what you have to analyze, right? Okay. So now once you have inserted a dielectric material between the capacitor plates in this case, right? So what will happen here? See, in this experiment you have to keep one point in mind, that is V is always what? V must be always fixed, right? Okay, so that's what you have to keep in mind. In case 2 V is fixed, in case 1 Q is fixed, right? Okay. Now you can analyze on your own here, right? Okay. So the first one is V. So V is equal to what? V is equal to E into D. So whatever happens in this experiment, V must be fixed. V must be fixed. Now here we are not changing the distance between the capacitor plates here. D is also fixed here. D is also fixed. Right? D must also be fixed. So if D is also fixed, then E must be what? Since V must be fixed, here E must also be what? E must also be fixed. Then only V will become fixed. Yes or no? Okay. But here we have to analyze why E is becoming fixed or why E is becoming constant in this case. So that's what you have to check. Right? Okay. So we know that the electric field between the capacitor plates, E is equal to what? E is equal to rho s by epsilon. Right? Rho s by epsilon. Rho s by epsilon, right? Now, now in the previous case, epsilon is equal to epsilon naught. Now what you have done? You have inserted a dielectric material whose permittivity epsilon is equal to epsilon naught into epsilon r. So that means here epsilon has increased here. Epsilon has increased by epsilon r times when compared to this one. Yes or no? So whenever epsilon increases, what happens here? Electric field is going to decrease. The electric field is going to decrease. Yes or no? Now we know this V is equal to what? V is equal to E into D. So here D is not changing. D is fixed. Understood? Whenever you insert a dielectric material here, since epsilon is increasing, the electric field will try to decrease. So once the electric field tries to decrease here, then potential will also tries to decrease. Right. Now here the potential is trying to decrease here. So which means here the potential, the battery potential will become greater when compared to this capacitor potential. So in that case, what will happen? The charge transfer will take place from the power supply or from the battery to what? To the capacitor. So it will never ever allow for the potential to change here. Always it tries to maintain the potential across the capacitor must be fixed. Understood? It will never allow for the potential to change. So whenever it is trying to decrease, what happens here? Since the potential here is trying to become lesser when compared to the potential of the battery, what will happen? So this battery is going to supply the charge to the capacitor. Understood? So this battery is going to supply the charge to the capacitor. So that means on the capacitor plates the charge is going to increase. So the charge is increasing means rho s is also going to increase. Okay. So here epsilon is increasing and rho s has to increase by the same proportion. Here rho s is also increasing. So if rho s increases, the electric field will also increases. So if the electric field increases, then the potential will also increases. Understood? Okay. So if this increase and decrease are in the same proportion, then what will happen? V will become fixed. The electric field will also become fixed. D is also fixed. Yes or no here? Okay. Okay. So that's what you have to understand here. And one more conclusion we can make here is so from here I can say E is fixed. Yes or no? E is fixed, which is equal to rho s by epsilon. So from here I can say rho s is proportional to what? Rho s is proportional to epsilon. Right? So whenever the permittivity changes, correspondingly rho s is also going to change in this experiment. So that's what you have to keep in mind. So in this manner the electric field here is also what? Is also fixed. Okay. This is very important here. in this experiment the electric field is also fixed, right? Okay, so even though epsilon is changing, the electric field is fixed in this experiment. Why means whenever epsilon is changing, correspondingly rho s, that is the charge density on the capacitor plates, is also going to change in such a way that it is going to maintain the electric field as constant, right? So this is very, very important here. This electric field is fixed in this experiment. So this is very, very important, right? Okay. So I hope this is crystal clear here. Next, second one is electric field, right? So we have already analyzed about electric field. So electric field is fixed, yes or no? So electric field here is fixed here. E field is fixed. Fixed means constant, it is not going to change, right? Okay. Next, third one, what happens to capacitance? So capacitance, C is equal to what? C is equal to Q divided by V. Here in this experiment the potential is fixed, so Q can change, so which means C is proportional to what? C is proportional to Q, right? Okay. Okay. Right? Okay. Next, fourth one. So we will see what happens to energy. So energy is equal to what? Half into CV square, which I can represent as half into Q into V. So here V is fixed. So I can say here the energy is proportional to what? Is proportional to Q, right? Okay, energy is proportional to Q. So you can easily analyze in this manner here. See, since Q is proportional to rho s, yes or no? Since Q is proportional to rho s, we can say C is also proportional to epsilon. And here, since Q is proportional to rho s, we can say energy is also proportional to epsilon. Understood? So in this manner we can link one and other, right? So I hope this is crystal clear here. So these are the four experiments. Which are very, very important. So based on this, many conceptual questions have been asked in PSUs and in GATE exam and also in engineering services exam, right? Okay. Okay. So now I will give you one question here. So we have analyzed 4 experiments, that is under case 1 we have analyzed 2 experiments and in case 2 we have analyzed another 2 experiments. So totally 4 experiments. So in case 1 they have connected the capacitor to a power supply. So once the capacitor has been charged, then the power supply is removed. So in this case the charge on the capacitor plates will get trapped, which means Q is going to be fixed. Throughout this experiment Q is going to be fixed. Understood? Okay. So now we have observed what happens to potential, electric field, capacitance and energy stored in the capacitor if the distance between the capacitor plates is changing. Then we have analyzed what happens to V, E, C and W if you insert a dielectric material between the capacitor plates. Understood? So under case 1 we have analyzed these 2 experiments. Next, in case 2 you have connected the capacitor to a power supply. Now the power supply is not removed here. You have charged the capacitor, but now the power supply is not removed. So the power supply is still connected to the capacitor, which means always the potential across the capacitor is equivalent to what? Is equivalent to battery potential. So which means the potential in this case must be fixed. Understood? So under this condition, what happens? What happens to V, E, C and W if you change the distance between the capacitor plates? And what happens to V, E, C and W if you insert a dielectric material between the capacitor plates? So this is the analysis we have done. Understood? So I am saying that don't remember whatever we have done the analysis, don't try to by heart those things. Understood? So you have to get familiar with the analysis, right? So whenever they have given the problem, you have to identify it will come under case 1 or case 2, experiment 1 or experiment 2 or experiment 3 or experiment 4. So that's what you have to identify. So once you have identified that one, then it is going to be very simple to solve that problem, right? Okay. So now here I will give you one homework problem here. I will give you one homework problem. So write down. So this is previous IES question. So if you tell the answer now itself, it is very good. Okay. So here consider the following statements. Write it down here. Consider the following statements. A parallel plate capacitor is filled with dielectric of relative permittivity epsilon R1 and connected to a DC voltage of V volts. If dielectric is changed, to another, with a relative permittivity, epsilon R2 is equal to 2 times of epsilon R1, keeping the voltage constant. So which means they have not removed the power supply here, right? So they have charged the capacitor and now they have not removed the power supply. So that's what they mean, keeping the voltage constant, right? Then the first statement they have given as the electric field within the capacitor doubles. First of all, you have to identify under which case it comes, under what experiment it comes. So if you identify that one, then the problem will be very much simple, right? Okay. So this is first statement. And second statement, the displacement flux density D doubles. The displacement flux density D doubles. D is displacement flux density here, right? Here, right? Next, third one. The charge Q on the plates reduced to half. The charge Q on the plates reduced to half, right? So next, fourth statement, the energy stored in the capacitor is doubled. The energy stored in the capacitor is doubled. Okay. So select the correct answer using the codes given below. So select the correct answer using the codes given below. Right. So option A 1 and 2, option B 2 and 3, option C 2 and 4, option D 3 and 4. Okay, so that means which of these statements are correct. So that's what you have to determine. That's it. So they have given that consider the following statements. A parallel plate capacitor is filled with a dielectric of relative permittivity epsilon R1 and connected to a DC voltage of V volts. If dielectric is changed to another with a relative permittivity epsilon R2 is equal to what? 2 times of epsilon R1, keeping the voltage constant. Keeping the voltage constant. So which means they have not removed the power supply here. So the power supply is still connected to the battery. Understood? That's what you have to understand. And here they have changed the dielectric medium between the capacitor plates. So previously the dielectric medium between the capacitor plates is having the relative permittivity of epsilon R1. Now the relative permittivity between the capacitor plates has become equal to what? Epsilon R2, which is equal to 2 times of epsilon R1. So that means the relative permittivity between the capacitor plates has doubled here. Now it has doubled. Understood? So under this condition, they have given different statements. So now you have to identify the correct statements. So in first statement they have given as the electric field within the capacitor doubles. In second statement they have given the displacement flux density D doubles. In third statement they have given the charge Q on the plates reduced to half. In fourth statement they have given the energy stored in the capacitor is doubled. Select the correct answer using the codes given below. So which is the correct option here for this one? Case 2, second case. Very good. Very good, Srikar Reddy. Okay, so it will come under case 2, second case here. Yes or no? Okay. Okay. So in case 2, second case. So that is this is the capacitor and you have connected to the power supply. So the potential across the capacitor will be what? Will be fixed, right? And here this is plus and here it is minus. Now here they have inserted a dielectric material between the capacitor plates, right? Now here epsilon is equal to what? 2 times of epsilon R2. Epsilon R2 is equal to 2 times of epsilon R1, right? So that means epsilon value has increased here. Epsilon value has increased. So that means epsilon has doubled. Epsilon value has doubled. Understood? So in that case, what happens to the electric field within the capacitor plates? Tell me what happens to electric field between the capacitor plates? In the first statement they have given the electric field within the capacitor doubles. Is it correct here? Do the electric field within the capacitor plates doubles in this one? You have to first identify it will come under case 2 and experiment number 4. Yes or no? Okay. Okay. So in that case the electric field within the capacitor plate, they have given it as electric field within the capacitor plate doubles. So whether this statement is correct or wrong? So this is wrong here. So first statement is wrong. You can eliminate that. Yes or no? Okay. Okay. So we know that the electric field is equal to rho s by epsilon, right? So and V is equal to what? V is equal to E into D. So V is fixed. Here D is fixed. So E must be what? E must be fixed. So for E to be fixed, so here what is happening? Whenever you insert a dielectric material, here epsilon is increasing, right? So whenever epsilon increases, rho s has to increase by the same proportion. So then only the electric field will be fixed. So that means here the charge on the capacitor plates is increasing here. The charge on the capacitor plates is increasing. Understood? Okay. Okay. So the electric field within the capacitor doubles. Electric field is fixed. It is not going to change. So first statement is wrong, and the charge is increasing, right? If you observe the third statement here, the charge Q on the plates is reduced to half, but here the charge on the capacitor plates is increasing, right? So which means you can eliminate this third statement also, right? Okay. Now what is the correct answer? If you eliminate 1 and 3, what is left out? 2 and 4, right? And we will check why this 2 and 4 are correct. We will check that also. So in second statement they have given the displacement flux density D doubles. So displacement flux density, we know that D is equal to what? D is equal to epsilon into ER. So now in this experiment E is what? E is fixed. In this experiment E is fixed. Understood? So what happens to epsilon here? Epsilon has increased here. Yes or no? Epsilon has get doubled. So if epsilon doubles, the displacement flux density is also going to get doubled, right? Okay. So that means statement 2 is correct. Statement 2 is correct. Next, in fourth statement they have given the energy stored in the capacitor is doubled. So the energy stored in the capacitor here, the energy stored in the capacitor. So what is the energy stored in the capacitor? So that I am representing with W, which is equal to what? Half into, I can write it as Q into V. So here V is what? V is fixed. So W is proportional to what? W is proportional to Q, right? Okay. So here Q is proportional to what? Q is proportional to rho s, and here from this we can say rho s is proportional to what? Epsilon. Yes or no here? E is fixed means what? E is fixed means I can write rho s is equal to E into epsilon, and rho s is proportional to what? Epsilon. So since rho s, Q is proportional to rho s, I can say Q is proportional to epsilon. Q is proportional to epsilon. Understood? So if Q is proportional to epsilon, I can say energy is also proportional to what? Epsilon. So since here the permittivity is getting doubled, the energy is also going to double, right? Okay. So in this manner we can analyze here. So option 4, statement 4 is also correct. So that means 2 and 4 are correct. 2 and 4 are correct. So for this question 2 and 4 are correct. Option C is correct for this question. So option A is wrong, option B is also wrong, option D is also wrong. So for this question option C is correct. Okay. Okay. So in this manner, first of all you have to understand here under which case, under what experiment it comes. So once it strikes to your mind, then you can analyze it in a very simple manner. Okay. Okay. So it is not at all homework problem now because I have solved it, right? Okay. So now with this I am winding up the session for today, and with this I am winding up the capacitors topic here, right? See, from tomorrow onwards, what I am going to do is from tomorrow I am going to start uniform plane waves. So this is only for what? This is exclusively for EC students. So it is not present for electrical and instrumentation students. So from tomorrow onwards I am going to start the syllabus for EC students, exclusively for EC students, right? Okay. Okay. So tomorrow the class will be at 7:30 p.m. 7:30 p.m. So EMT class will be at 7:30 p.m. and tomorrow I am going to start uniform plane waves, which is exclusively for ECE students, right? So from tomorrow onwards here I am going to cover EC topics, right? Okay. 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 So with this, I am winding up the session for today. So tomorrow we will meet exactly at 7:30 p.m. and we will start a new topic, that is uniform plane waves, which is exclusively for EC students, right? So we will meet tomorrow exactly at 7:30 p.m. So until then, take care. Bye bye.